In this video, we're going to be thinking about binary numbers, but before we start, one thing you've got to remember is that computers have got no brain. They're just a bunch of switches. But the patterns that those switches make can be used to represent numbers, pictures, sounds, instructions, perform calculations, anything that we want. As long as we know what the pattern represents, then we're okay. So this circuit is actually showing a way in which we can use a series of switches and some transistors to turn on and off light bulbs, and those light bulbs can be used to represent parts of a number. Now, humans aren't very good at writing down the states of switches by drawing pictures of switches, so what we tend to do instead is use a number system, and the number system is called binary. And if a switch is off, we represent that with a 0, and if a switch is on, you represent that with a 1. Okay. If you look at the on-off switch on any electronic device, you'll see part of a 0 and a 1 in it, and that's kind of the on-off bit of the switch. Now, this is in base 2, in fact, and we'll look at what that means in a little bit later in the video. Those switches, via some transistors and some wiring, can turn light bulbs on and off, and each of those light bulbs represents a number. Light bulbs can be used to build up a denary number or a base 10 number. As long as we know what the light bulbs are worth, we can do it. So, if the light bulb's off, it's worth 0. If the light bulb's on, it's worth its value. So this is 0 plus the light bulb's on, so that's 8, plus the light bulb's on, so that's 4, plus the light bulb's off, so that's 0, plus the light bulb's on, so that's 1. And if we add those together, we get the number 13. 13. This is in base 10, and again we'll look at what that means in a sec. But bear in mind, this pattern of switches here, represented by this binary number 01101, can be used to store the number 13 if each of those switches is worth, or lights up a bulb, or turns an LED on, or whatever, and each of those devices is worth those numbers. So this is just one way we can use binary. So, but considering we're talking about binary numbers, let's have a step back and let's think about what numbers actually are. So first of all, we'll look at base 10. Base 10 is the number system that we use. It's called base 10 because it's got 10 possible digits in it. 10 digits. And you'll know what these are because this is the base, the number system that we use. The numbers that are in a base 10 number system are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Each of those digits represents a quantity of stuff. It just means that because there are 10 digits in there, 0 to 9, we can represent quantities in slightly less numbers. That's all it means. So let's have a look at a number and see how it's constructed. We'll choose a random 4-digit number in base 10. 3, 5, 1, 6, completely at random. This is in base 10, and you represent the number being in base 10 by putting a little 10 next to it. As what's called a subscript on the right hand side. Starting on the right hand side, the first place in any number is always worth 1. It's the units place, or the ones place if you want to call it that. Now, because this is base 10, and I can actually represent 9 things using a number in this place, if I want to represent 10 things, I haven't got a symbol for 10 things, so I have to use 1 in the next place up. So in fact, this one is worth 10 times as much as that. So that's worth 10. So each one of those is worth 10. This is making sense because you know these number systems and how they work because you use them all the time. If I get to 99 here, I haven't got any more numbers to represent anything bigger than that. So I have to use a 1 in the next place. So this is again worth 10 times as many, or 100. And again, if I get to 999, I haven't got anything to represent 1,000 in 3 digits, so I have to use a 1 in the next place. So the next place is worth a 10 times that, which is 1,000. Which is 1,000. Okay, so, and you times it by 10 because it's a base 10 number, because I've only got, you get the idea, hopefully. Right, let's have a see what this actually means in practice, and you'll be like, wow, well, this is obvious. This is really obvious, I understand this, but that's fine, because I'm kind of taking us back to something we do understand before I talk about something that we might not. This represents 3 times by 1,000. Tiny writing, which that's like a 6. 3 times 1,000 is 3,000. All right, and yeah, I get that, sir. It's fine. This represents 5 times 100. Okay, which is 500. I get that. 500. That's okay. I understand that as well. This represents 1 times 10. Hopefully that makes sense. 1 lot of 10. And that's 10. Yeah, good. This represents 6 lots of 1. That is a 6, by the way, which is 6. And if I add, this is, all I'm doing is partitioning the numbers now. If I add those together, no prizes. For guessing that was up to 3,516. Now, this is in base 10. It's in base 10 simply because we used base 10 up here to represent the place values, so that wobbly arrow, to represent the place values for the number. Let's look at a number system that isn't base 10 now, and it kind of makes sense to use base 2, which is binary, which is the way that we represent the state of the switches in a computer. And once you understand binary, you kind of hopefully understand how computers represent things using switches. This is where we're heading. So let's have a look at this. This is base 2. Base 2. This is called base 10 because it's got 10 digits. This is called base 2 because it's got 2 digits. 2 digits. And now the only 2 digits we've got are 0 and 1. Okay, that's not much. We can't do much with 0 and 1 apart from have it or not have it. And actually this makes binary super easy to use, super easy to understand, super easy to do maths with. It really is a very straightforward number system. Let's start by putting a completely random binary number into this grid. Remember that we've only got the digits 0 and 1 available to us in this base because we're representing the states of switches and they can only be on or off. This is almost like representing the state of a switch that can have 10 different positions, 0 off, and then a series of voltages from 0 through to 9 volts or something. And you could do it. You could have a computer that does that. It's just that the electronics will get really complicated. So it's much easier and much less error prone to represent the value is either on or off because the switch is either on or off. It's difficult to tell whether the switch is half on or half off, and certainly whether it's a 1/10 on or 2/10 on. It's quite tricky to do that. So that's why we use switches that are, well, that's what the digital systems are. Anyway, that's besides the point. Let's put a random binary number in here. Remember, this represents 4 switches. The first one's off. On, off. So that's what that's actually representing, but we write it down like that in base 2 because, you know, it's easy. In the same way that in a base 10 number, the first right handmost place is the units place, this is also the units place as well. But if we increment this number to 1, fair enough, if we add another one to it, we haven't got a 2, we've run out of numbers already, which means that I need to increment the next place, which is exactly the same as I would do here if I got to 9. So, in fact, just like in the denary number, this was worth 10 times. This is now worth 2 times the previous one. So this is worth 2. And when I get to 1 1, all right, which he's covering his mouth and saying that's 3, but it's not really 3 because it's binary 1 1. I run out of numbers again because I haven't got a 2, so I have to increment the next place. So that's actually worth twice as much of that as well, so times 2. So if I kind of got to 3 here, if I was thinking in denary. 4 I haven't got, I can't represent 4, I can represent 3 because that's 1 lot of 2 and 1 lot of 1 added together. I can't represent 4, so I have to use the next place. So that's worth 4. Okay, and we carry on with the pattern. So this is times 2. So when I get to 1 1 1, I can't represent anything bigger than that. So I've got to go to the next place and increment that, and I get 8s. Now, in fact, because you've either got or you haven't got, because it's either on or off, these are dead easy to do the maths with. So to add up these numbers and find out what they actually represent is fine. One thing you've got to be aware of, however, is that these numbers that I'm using here are base 10 numbers. Base 10. So when I perform this calculation under here, I'm converting binary into base 10 because I'm using base 10 numbers as the place value headers. Anyway, let's have a look at this one. This actually says 0 times 8, which is 0. This says 1 times 4, which is 4. This says 1 times 2, which is 2. And this says 0 times 1, which is 0. And if I add these together, I get 6. 6 in base 10. Now remember, this is only in base 10 because I've used base 10 numbers for the headings on these columns. So bear in mind, you know, that's kind of how, that's why you can use this method to convert binary numbers or patterns of switches, we've got to keep coming back to that and remember that, into one possible interpretation of those patterns, which is as a number. Alright, you might want to pause the video, rewatch a bit, think about that, have a chat to somebody, and consider what we've just done there, because you know, it's yes, it's familiar, and yes, it's unfamiliar. If you really want to stretch yourself, you could try thinking about other number bases as well. I wouldn't go bigger than 10, because that's, you know, we run out of symbols then for it's difficult. So you know, you could think about other number bases, maybe between 2 and 10 if you want to. But pause the video if you want, and then I'll speak to you in a sec. Well, if you did pause the video, then we're back. If you didn't pause the video, I'm still here. Let's now think about how we perform addition, how we add numbers together. Now, adding numbers together in base 10 is again about thinking about that idea that if I get a number that's too big to fit into one of the places, I have to perform some carry operations, and this will help you when it comes to adding binary numbers together. And that brings in a whole heap of stuff around the way that computers do maths, okay, which is what we're coming on to at the end of this video. I'm taking you a long way here, but I think you're up for it. Okay, let's have a look first of all at the way that base 10 addition works. So we'll go with base 10. Oops, I'm in the wrong colour. Doesn't matter, I'm not restarting. Base 10. Base 10 numbers. Okay, remember that base 10 numbers have got 10 digits to represent things. And those digits are 0 through 9. I'm not going to write them all out again. 0 through 9. So let's look at some additions. Let's look at some sums, if you want to call them that, using base 10 numbers. Now, I've got quite a lot of options here because I've got 10 different numbers I could use. When I'm adding two numbers up, I've got like 100 different combinations of those. So I'm going to choose some. I'm not going to choose all of them. I'm going to choose the range of numbers. So I'm going to start with the first. I'm just going to add two numbers together. I'm going to start with the first number being 0, and I'm going to add the lowest digit I can use, which is 0. I'm going to add those two together and we'll get 0. Ovs. Then I'm going to go right in the middle of the range of numbers that I've got available to me, and I'm going to do 0 plus 5. Okay, so that's right in the middle of my range of numbers here. 0 plus 5 is 5. Fair enough. And then I'm going to go right to the end of the range of numbers that I can use, which is 0 plus 9, and I'm going to get 9. Alright, that's straightforward, okay, that's fine. I'm never going to get an answer that's bigger than 9 if I do this, simply because I'm adding a number to 0, therefore I can't get a number that's bigger than 9. But let's consider what happens if we do get numbers that are bigger. So I'm just going to now choose a different number for the top, so we'll go with 3. Okay, I'm going to go with 3. I'm going to start with the bottom, middle and top of the range for the second number, so I'm going to put 3 plus 0. 3 plus 0 is 3. Gosh, I had to work that out. Let's go in the middle of the range. 3 plus 5. I said 3 and wrote 0. Well, that's okay. 3 plus 5 is 8. That's alright, because that's not bigger than 9. So I can fit that in one place. Let's go 3 plus 9 now. Now, the problem is, this adds up to 12, but I haven't got 12 available. I haven't got a digit that represents 12, so I need to put a 2, and I'll just put this line under it. I need to put a 2 and then carry a 1 into the next place to represent the 10. I haven't got anything to add to the 1 here, so I can just put the number there, the 1 in there, and that represents 12. Now remember, I have to do this simply because the answer here is bigger than 9. So it's bigger than the biggest digit I've got available to store in one position in my number. Alright, so that's denary base 10 numbers. We get that, hopefully, because that's the same maths that we do every day anyway. Let's have a look at binary, which again is a little bit different, but if you apply the same rules, you'll see that the behaviour is exactly the same, and hopefully you should, fingers crossed anyway, you should see that this works exactly the same way. So let's look at base 2 numbers now. So base 2, it's called base 2 because I've got 2 digits, and those digits are 0 and 1. There's only 2 numbers, so there isn't a middle of this range. There's a lowest number and a biggest number, but nothing in between. So that actually makes things again much easier because there's only a limited number of numbers I can add together. So I can actually learn all the rules for binary addition, rote learn them if I want to. It's better to work out how to do them than to rote learn them, because then you can work in any number base you want. Let's look at the lowest number that I can use in here. So I'm going to say 0, first of all, plus naught. Okay, that's the same. And it's the same as it is here, right? It's the same as it is there because naught's in both numbers systems. So that's why it looks the same. Let's go to the... Well, there's no middle of the range. There's just an upper part of the range because there's only two numbers. So the biggest number I can use is 1, and that's 1. Okay, again, if I'd use that as an example for base 10, it would be the same because 0 and 1 are in both number bases. Right, okay, so let's say now, let's say you choose another number for the top one. Well, the only other number I've got available I haven't used is 1, so I've got to use 1. So let's add 0 to that, and that comes out as 1. Okay, well, that's the same as this one, fine. Let's now use the other number I've got, 1 plus 1. Hang on a minute. I haven't got enough numbers to represent this. So essentially, I've got to put 0 in there, and I've got to carry the 1 across. This is 1 lot of 2, so it's 1 in the 2's place. And therefore, because I've got no other numbers to add up there, I can put this. Now let's just think back now. Let's look back at the conversions and think about exactly what that number represents. Because when I look at that, I see 1, 0. I don't see 10. And the only reason I don't see 10 is because I know that this is a base 2 number. Now, it's important, I think, if you're working in multiple number bases to write down the base next to it because, as you've seen here, 0 and 1 are common in both number systems. If I only use 0 and 1, I could be working in base 10, I could be working in base 2. So really, technically, I should go back and I should write a little number 10 there. I should write a little number 10 next to all of them, really, but we'll just do this. So that I'm under no illusions that this is base 10. Okay. Again, if you don't see that, it's not massively important as long as you appreciate that sometimes a number in one number system can look like a number in another one if the numbers are common. So this looks like 10, but it isn't. And don't ever call it 10 because it's not. It actually represents, and if you think about the number grid, 1 and then 2. So this is just part of that grid that I drew up here. It's these first two columns in this grid here. That's all I'm doing. And I'm saying, right, okay, well, this number is 0 and then 1 in there, which is actually 1 times 2, which is 2. I had to work that out. And then 0 times 1, which is 0. And then I add those together. That looks like 20, which is even more confusing. That's actually 2 in base 10. Right, and again, bear in mind, that's 2 in base 10. I've converted it to base 10 because these are base 10 numbers up there. So just bear that in mind. Now, interestingly, there is one more thing I want to show you here. One more rule, if you like, of adding binary numbers together. There's only 5 altogether, so you can remember all these. It's not an issue. The fifth one I haven't shown you is this. Let's say there's a situation where I'm adding a binary two binary numbers together, 2 binary digits together, but I'm in the middle of a number and I've got a carry from a previous number. This could look like this. It could look like 1 plus 1 plus 1. Okay, it could look like that. When I add those together, it like comes to 3. Now I know I ran out of numbers when I got to 1. So and I had to carry 1 across into the 2's place at that point. So I've carried 1 across into the 2's place, and I've still got 1 left. So I should really put a 1 there, and it should be 1 carry 1, and put the 1 there. Now that looks like 11. It's not 11. It's 1 1 in base 2, 1 1 in binary. Again, let's think about what that means if I construct the number and by converting it into denary. Using denary numbers as the column headings. Let's put a 1 and a 1 in there, and let's convert these. That's 1 times 2, which is 2, and this is 1 times 1, which is 1. If I add those two together, sorry, that's meant to be a plus sign. If I add those two together, I get 3 in base 10, which is kind of obvious. 1 plus 1 plus 1. This is the same number of things as 3 in base 10, but the same number of things is represented by 1 1 in binary. I hope you're not confused. You've got to think about this. You might have to think about this a little bit more. Now, the last thing I'm going to do is show you a little trick, a machine that I've invented called, and you'll be impressed with this, called the ACME 5-bit Full Adder. Right, now this is a hint at an electronic circuit that at some point in your life you might come across, and you might construct one of these if you ever become an electronics engineer or you study computer science at higher levels than this. This is a 5-bit full adder, and using these ideas, these rules, I can show you how we can use an electronic circuit to add two numbers together. This is magic. Okay, so just bear with me a sec, and just think about this. Let's have a go anyway. Let's choose two random binary numbers to put in here. Remember, I'm actually using these binary numbers now to represent denary numbers, so I'm not using them to represent pictures or sounds or instructions or anything like that. I'm using them to represent actual denary numbers, because remember, we can't store denary numbers in a computer directly. We've got to store them as patterns of switches, and we've learned how to do that hopefully anyway. So let's put some numbers. Let's put a couple of binary numbers in here. I'm going to store 0. I'm just making these up. 0, but I'm doing it on purpose so that I've got a fairly small answer to my sum that I'm going to perform in a minute. And let's choose another one. So I'm going to put some zeros at the left hand side just so that I know that I'm not going to get a bigger number than I can store. A little challenge for you is to work out the biggest number I can store using 5 bits, 5 switches. Got that. Now, just as a little aside here, let's just I've got to match my colours. So I've got to match my colours. So let's think about what these actually represent. If they represent, let's put the place values. That's a 16. Okay, that's an 8. This is a 4. This is a 2, and that's a 1. Okay, and that's a 1 over there. So in fact, if I was going to convert this to binary, this is pause 3. Correct. Well done. This second number, again, I've got to match my colours. This is where can I write these? I'll write them here. I'll write them here. They're not in this line, but I'll write them here anyway. I'll write them here. 16. This is the 8. This is the 4. This is the 2. And this is the 1. So if I was going to use this pattern to represent a denary number, it would be, correct, 7. Well done. So I'm adding 3 and 7, which means I should get 10. Well, let's see if that works. Fingers crossed it will work anyway, but we'll see. Now, let's think about the rules here. Let's take 2 digits at a time, so 1 digit in each column. These are meant to be in the same column, but I've just separated them so that you can see them a little bit easier. So if I say, right, okay, 1 plus 1, if I use my rules, which are up here somewhere, 1 plus 1 is 0, carry 1. I'm not going to keep going back to those, but I'm just going to show you. 1 plus 1 is 0, which is the sum part, and then 1 is the carry. So with that little c means carry. That 1 then goes into this magic box that adds the numbers together, and I've got a 1 plus 1 plus 1, which is 1, carry 1. This number goes into this box. I've got a 1, a 0, and a 1 added together. That's 0, carry 1. I've got now a 1 going into this box, and I've already got 2 zeros going in, so 0 plus 1 is just 1. The carry there is 0. There's nothing to carry, because I can fit 1 in one place. I've got a 0 and a 0 and a 0, and if I add those together, I get 0, carry 0. I'm trying to show you now how I can use an electronic circuit, because I wasn't thinking about what I was doing. I was applying a set of rules to what goes on inside those boxes there, the adders, if you like. Just applying a set of rules, not really thinking, because remember, computers can't think. Throwing some numbers in, using the rules, and putting numbers out of those, and numbers come out of the boxes. Input, some processing, some output, and so on and so forth. So I've got an answer. Don't know whether that answer's right, but we'll give it a go. I'll just choose my colour again, because you know I've got to, and think about what these represent. That's a 16. That's an 8. That's a 4. That's a 2, and that's a 1. Okay, that's going to help us in a minute. So let's try and put this number into a grid and see if we get the right answer as well. So this is not using this, but representing it as a little grid. So let's put the numbers in first of all. Do I need to choose my colours again? I don't think I need to be honest. I think I'm alright. No, I'm going to do it. I'm going to go back on it. I'm going to choose my right colours here. There you go. Let's choose. Oh, I didn't do it. Let's choose that one. That's okay. So let's put my first number in. What was it? 00011. So let's put 0, 0, 0, 1, 1. Remember, that's in base 2. Okay, that's all over there. Now let's just add this up. That's 1, 2, 4, 8, 16. Okay, so that's 3 in base 10. Hopefully we're getting used to doing that now. Let's have a look at the second number that we got. Choose my colours. Got to match my colours. And let's go. And that number was, I think, 0, 0, 1, 1, 1. Okay, just going to go back a sec, just rub those out. Because you know what I did wrong? Should have done them in black. 1, 2, 4, 8, 16. No particular reason, just, you know, how it is. And then finally, we'll add these together. Now, let's choose my colour. Let's go through the rules again. 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1. 0 plus 1 plus 1 is 0, carry 1. 0 plus 0 plus 1 is 1. 0 plus 0, no carry. 0 plus 0 is 0. Let's work that out. Ooh, I missed out doing that one, didn't I? So let's do that. Got to pick my colour from there. Got it! Okay, this is in base 2. This is 4 plus 2 plus 1 is 7 in base 10. Right, so let's go back and let's have a look at this number here we've got here. Didn't actually click the colour picker then. There we go. Right, this is in base 2 again. This is 8 plus 2 is 10. So it kind of works, okay? Now, applying the rules, all I've done is apply the rules. I've tried to introduce you to an electrical circuit. This is a circuit, and you can build this with electronic components. I promise you can. And you can flick switches on and off. And if you flick those switches on and those off and those on, the light bulbs will light up if you use the right electronics in there, and it'll give you the answer. It's magic. It's not doing any maths. All it's doing is following a set of rules, and the rules are defined by the electronics, and the electronics work out the answer. Now, all that circuit can do is add two numbers together. And again, this is something that you've got to realise, is that if you design a circuit to do one job, it will do that job and it will not do any other jobs. So again, do bear that in mind. Now, you might want to pause the video again there before we move on. Give yourself a bit of a break. Come back to that in a second, and we'll think about. We'll go through some examples. I'll give you some examples to try as well. So you might want to just pause the video and have a little bit of a break there. Okay, if you pause the video, welcome back. Let's just go through a few examples. So I'm just going to go through a few for us to try together, and then we'll see if we can do it. And I'm going to again write some questions out. You have a go at them, and then you have a go at them, and then I'll go through the answers with you. So I'm just going to pick again some random binary numbers here: 0, 1, 1, 0, 0, and I'm being very careful to make sure that these numbers aren't too big, so I know I can store the answers using 5 digits. 0, 0, 0, 1, 1. Now, again, you're not going to perform any actual conversions here. You're just going to purely follow the rules of binary addition. So that's A. We'll go with the second one here. You can write these down if you want to on a piece of paper. 1, 1, and then plus 1, 0, 0, 1, 0. And then we'll just, okay, we'll do that, and we'll do this. Let's do another one. Let's give you 4 to do. 0, 1, 1, 0, 1, 0, 0, 1, 1, 1. Add those together. Right, again, just quickly leave those there. And then D, last one, 0, 1, 0, 1, 1, and the second number is 0, 1, 1, 1, 1. Add those. I'm being really careful here to leave what's called the most significant bit, either 0 if I know that I'm going to get carries into it, or if I know I'm not going to get a carry, I'm leaving it there. So again, what I suggest you do, pause the video at this point, have a go at those, and then come back in a couple of minutes, and I'll go through the answers with you. So pause the video now, and we're back, and hopefully we'll go through the answers to these very quickly. 0 plus 1, just applying the rules. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. I have to work that out. 1 plus 0 is 1. 0 plus 0 is 0 in base 2. Remember, it could look like a denary number, but it's not. So it's quite useful to just put the number base by the next of it. By there. Right, second one, the next of it. The second one, let's apply the rules. 1 plus 0 is 1. 1 plus 1 is 0, carry 1. So I'm going to make sure I've got my carry in. 0 plus 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. Again, this is a number in base 2. C, 1 plus 1 is 0, carry 1. 0 plus 1 plus 1 is 0, carry 1. Aha! 1 plus 1 plus 1 is 1, carry 1. 1 plus 0 plus 1 is 0, carry 1. 0 plus 0 plus 1 is 1, again in base 2. And lastly, 1 plus 1 is 0, carry 1. 1 plus 1 plus 1 is 1, carry 1, correct. 0 plus 1 plus 1 is 0, carry 1. And finally, because I've got nothing else to do here, 1 plus 1 plus 1 is 1, carry 1. And, well, not finally, obviously I've got to add the carry in. 0 plus 0 plus 1 is 1 as well. That kind of gets us up to where we need to get up to. If you want to think about this a little bit more, you could try converting these numbers into base 10, into denary, just by using the place values and just adding up the numbers. And just convince yourself that those actually represent the same quantity of things as they would do if you were adding two base 10 numbers together. Anyway, thanks so much. Sorry that's lasted so long, but hopefully we've been through everything that we need to know about binary numbers, and also considered how computers use electronics to perform maths, because that's how they do it. Thanks again.